Hey everyone, welcome to the Chem Wizard podcast, your place for learning and listening to the magic of chemistry on the go. Grab a snack, maybe some coffee, and let us begin our adventure. This podcast is for the students that is walking to class and perhaps wants something to listen to fill that time. Absorb that 8 a.m. chem class that you may or may not have dozed off in. Listen to your chemistry lesson on the go, listen to info passively, or just simply learn something new. My goal as your personal chem wizard is to make your first general chemistry class as approachable and enjoyable as possible, so you'll want to stick around for organic chem and your other courses. Being a student, or rather a wizard, can be difficult, but it doesn't have to be impossible. It can be a magical experience. In this second episode, we will dive straight into the next lesson of the Pearson General Chemistry curriculum, which is all about atoms and elements. So atoms, what are they? The word atom comes from the Greek word atomos, I hope I'm pronouncing that right, which means indivisible. You can't divide a carbon atom into smaller pieces and still have the properties of carbon. Atoms compose all ordinary matter. If you want to understand matter, you must begin by understanding atoms. So modern atomic theory. The theory that all matter is composed of atoms originated from several observations and laws. The three most important laws, and I would highlight this, that led to the development and acceptance of the atomic theory are as follows. Number 1, the law of conservation of mass. Number 2, the law of definite proportions. And number 3, the law of multiple proportions. So let's start off with the first law, the law of conservation of mass. Antoine Lavoisier formulated the law of conservation of mass, which states the following. In a chemical reaction, matter is neither created nor destroyed. Hence, when a chemical reaction occurs, the total mass of the substances involved in the reaction does not change. So, in short, total mass of reactants equals total mass of products. This law is consistent with the idea that matter is composed of small, indestructible particles. Number 2, law of definite proportions. This states that all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. The law of definite proportions is sometimes called the law of constant composition. So for example, the decomposition of 18.0 grams of water results in 16.0 grams of oxygen and 2.0 grams of hydrogen, or an oxygen to hydrogen mass ratio equals 16.0 grams of O, or oxygen, in the numerator and 2.0 grams of hydrogen in the denominator, which equals 8.0 or 8 to 1. And number 3, law of multiple proportions, or Dalton's law. This states when two elements, let's call them A and B for now, form two different compounds, the mass of element B that combined with 1 gram of element A can be expressed as a ratio of small whole numbers. An atom of A combines with either 1, 2, 3, or more atoms of B. So for example, AB with subscript 1, AB subscript of 2, AB subscript of 3, etc. Therefore, the masses of B that react with a fixed mass of A are always related to one another as small whole number ratios. Carbon monoxide, so mono before oxide, and carbon dioxide are two compounds composed of the same two elements, carbon and oxygen. The mass ratio of oxygen to carbon in carbon dioxide is 2.67 to 1. Therefore, 2.67 grams of oxygen reacts with 1 gram of carbon. In carbon monoxide, however, the mass ratio of oxygen to carbon is 1.33 to 1, or 1.33 grams of oxygen to every 1 gram of carbon. Atomic theory. This states the development of the atomic theory of matter is based on law of conservation of mass, law of definite proportions, and law of multiple proportions. So Dalton atomic theory. John Dalton explained the previous 3 laws in his atomic theory of matter. Number 1, in the postulates, each element is composed of tiny, indestructible particles called atoms. Number 2, all atoms of a given element have the same mass and other properties that distinguish them from the other atoms of other elements. Number 3, atoms combine in simple whole number ratios to form compounds. And number 4, atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way that they are bonded. Discovery of the electron. Up to this point in time, scientists accepted that atoms were the smallest constituents of matter. J.J. Thomson, who lived between 1856 to 1940, developed cathode ray experiments. Thomson constructed a partially evacuated glass tube called a cathode ray tube. He found that a beam of particles called cathode rays traveled from the negatively charged electrode, called the cathode, to the positively charged electrode, called the anode. The particles that compose the cathode rays have the following properties. They travel in straight lines, they're independent of the composition of the material from which they originate, so the cathode, and they carry a negative electrical charge. Discovery of the electron. Continued. J.J. Thomson measured the charge-to-mass ratio of the cathode ray particles by deflecting them using electric and magnetic fields as shown in your textbook or whatever workbook you're using. The value he measured for the charge-to-mass ratio was negative 1.76 times 10 to the 8 coulombs per gram. So coulombs, the unit for it is a C, or a capital C. And I would highlight this number and put it on a cue card. Milikan's oil drop experiment, the charge of the electron. American physicist Robert Milikan, who lived between 1868 to 1953, performed his now famous oil drop experiment in which he deduced the charge of a single electron. By measuring the strength of the electric field required to halt the free fall of the drops, and by figuring out the masses of the droplets determined from their radii and density, Milikan calculated the charge of each drop. The measured charge on any drop was always a whole number multiple of negative 1.6 times 10 to the negative 19 power coulombs, the fundamental charge of a single electron. With this number in hand and knowing Thomson's mass-to-charge ratio for electrons, we can deduce the mass of an electron. So if we take the charge multiplied by mass over charge, we're left with mass because charge and charge from the numerator and denominator cancel each other out. So we take negative 1.60 times 10 to the negative 19 coulombs, that's the charge, multiplied by, we don't know the mass, that's what we're trying to figure out, so x grams in the numerator, divided by negative 1.76 times 10 to the 8 coulombs, we are left with 9.10 times 10 to the negative 28 grams. Structure of the atom. J.J. Thomson proposed that the negatively charged electrons were small particles held uniformly within a positively charged sphere. This model, the most popular of the time, became known as the plum pudding model, or the raisin muffin, chocolate chip muffin, whatever suits your fancy. Rutherford's gold foil experiment. In 1909, Ernest Rutherford, who lived between 1871 to 1937, who had worked under Thomson and subscribed to his plum pudding model, performed an experiment in an attempt to confirm Thomson's model. In the experiment, Rutherford directed positively charged particles at an ultra-thin sheet of gold foil. The Rutherford experiment gave an unexpected result, however. A majority of the particles did pass directly through the foil, but some particles were deflected, and some, approximately 1 in 20,000, even rebounded towards the source. Rutherford concluded that matter must not be as uniform as it appears. It must contain large regions of empty space dotted with small regions of very dense matter. Rutherford proposed the nuclear theory of the atom with 3 basic parts. Number 1, most of the atom's mass and all of its positive charge are contained in a small core called a nucleus. Number 2, most of the volume of the atom is empty space, throughout which tiny, negatively charged electrons are dispersed. And number 3, there are as many negatively charged electrons outside the nucleus as there are positively charged particles called protons within the nucleus, so that the atom is electrically neutral. So that leads us into the next topic, the neutrons. Although Rutherford's model was highly successful, scientists realized that it was incomplete owing to discrepancies in the measured masses of atoms. Later work by Rutherford and one of his students, British scientist James Chadwick, living between 1891 to 1974, demonstrated that the previously unaccounted for mass was due to neutrons, which are neutral particles within the nucleus. The mass of a neutron is similar to that of a proton, so approximately 1.673 times 10 to the negative 27th power kilogram. A neutron has no electrical charge. Hydrogen contains only 1 proton and no neutrons. That's something important to keep in mind. Helium contains 2 protons and 2 neutrons. The helium atom is 4 times as massive as the hydrogen atom, which makes sense based off its atomic mass. Subatomic particles. All atoms are composed of the same subatomic particles: protons, neutrons, and electrons. Protons and neutrons, as we saw earlier, have nearly identical masses. The mass of a proton is 1.67262 times 10 to the negative 27th power kilogram. The mass of a neutron is 1.67493 times 10 to the negative 27th power kilograms. And the mass of the electron is 9.1 times 10 to the negative 31st power kilograms. And 1 atomic mass unit equals 1.660540199 times 10 to the negative 27th kilogram. Keep in mind, you won't need to memorize many significant digits. I just memorized 1.66, 1.67. The charge of the proton and the electron are equal in magnitude but opposite in sign. The neutron has no charge. The mass of an atom is given in AMU, or atomic mass unit, is the sum of the number of protons and neutrons in the atomic nucleus. Electrons have so much less mass that they're assumed to have negligible effect. And 1 AMU could also be 1 U, 1 dA for Dalton, etc. So elements, defined by their number of protons. The most important number to the identity of an atom is the number of protons in its nucleus. The number of protons defines the element. The number of protons in an atom's nucleus is its atomic number and is given the symbol capital Z. So the periodic table. Each element is identified by a unique atomic number and with a unique chemical symbol. The chemical symbol is either a 1 or 2-letter abbreviation listed directly below its atomic number on the periodic table. So for example, the chemical symbol for helium is capital HE, The chemical symbol for carbon is capital C, and the chemical symbol for nitrogen is capital N. I'd recommend for the test to memorize the first 20 elements. It does come in handy to know their letters and also their masses. Isotopes. What are isotopes? All atoms of a given element have the same number of protons. However, they do not necessarily have the same number of neutrons. Atoms with the same number of protons but a different number of neutrons are called isotopes. For example, all neon atoms contain 10 protons, but they may contain 10, 11, or even 12 neutrons. All three types of neon atoms exist and each has a slightly different mass. The relative amount of each isotope in a naturally occurring sample of a given element is roughly constant. These percentages are called the natural abundance of the isotopes. Advances in mass spectrometry have allowed accurate measurements that reveal small but significant variations in the natural abundance of isotopes for many elements. The sum of the number of neutrons and protons in an atom is its mass number and is represented by the symbol capital A. So the capital A equals the number of protons, lowercase p, plus the number of neutrons, lowercase n. A second common notation for isotopes is the chemical symbol or chemical name, followed by a dash and the mass number of the isotope. So for example, we'll have capital X, which is the chemical symbol or name, whatever that may be, dash capital A, which is the mass number. So we can have neon, capital NE, dash 20, neon, dash 21, neon, dash 22, etc. So ions, losing and gaining electrons. The number of electrons in a neutral atom is equal to the number of protons in its nucleus, designated by its atomic number, capital Z. Atoms can lose or gain electrons and become charged particles called ions. Positively charged ions, such as capital Na with a plus sign in its power, are called cations. And negatively charged ions, such as capital F for fluorine minus, are called anions. And an easy way to remember this is remember that cats have paws, right? And paws sort of kind of alludes to positive, so that's why cations are always positive. So finding patterns, the periodic law and the periodic table. In 1869, Mendeleev noticed that certain groups of elements had similar properties. He found that when elements are listed in order of increasing relative mass, these similar properties reoccurred in a periodic pattern. To be periodic means to exhibit a repeating pattern. Mendeleev summarized these observations in the periodic law, and this states, when the elements are arranged in order of increasing atomic mass, certain sets of properties reoccur periodically. Mendeleev organized the known elements into a table, known as the periodic table. He arranged the rows so that the elements with similar properties fall in the same vertical columns. Columns are referred to as groups, and rows are called periods. Mendeleev's table contains some gaps, however, which allowed him to predict the existence and even the properties of yet undiscovered elements. Mendeleev predicted the existence of an element he called ecosilicon or EKA silicon. In 1886, ecosilicon was discovered by German chemist Clemens Winkler, who lived between 1838 to 1904, and he named it germanium. The modern periodic table. In the modern table, elements are listed in order of increasing atomic number, rather than increasing relative mass. The modern periodic table also contains more elements than Mendeleev's original table because more have been discovered since his time. Classification of elements. Elements in the periodic table are classified as the following: metals, nonmetals, and metalloids. We'll start with metals. Metals lie on the lower left side and middle of the periodic table and share some common properties. They are good conductors of heat and electricity. They can be pounded into flat sheets, so this is known as its malleability. They can be drawn into wires, known as ductility. They're often shiny or lustrous. They tend to lose electrons when they undergo chemical changes. So some pretty common examples are chromium, copper, strontium, and lead. Nonmetals lie on the upper right side of the periodic table. There are a total of 17 nonmetals. 5 are solids at room temperature, so carbon, phosphorus, sulfur, selenium, and iodine. 1 is a liquid at room temperature, bromine. 11 are gases at room temperature: hydrogen, helium, nitrogen, oxygen, fluorine, neon, chlorine, argon, krypton, xenon, and radon. Nonmetals are poor conductors of heat and electricity. They are not ductile and not malleable. They gain electrons when they undergo chemical changes, and generally their properties are opposite to metals. Some pretty common examples you'll see on your test are oxygen, carbon, sulfur, bromine, and iodine. And lastly, metalloids. Metalloids are sometimes called semi-metals. They are elements that lie along the zigzag diagonal line that divides metals and nonmetals. They exhibit mixed properties of metals and nonmetals, and several metalloids are also classified as semiconductors because of their intermediate and highly temperature-dependent electrical conductivity. The periodic table can also be divided into main group elements and transition elements. Main group elements, whose properties tend to be largely predictable based on their position in the periodic table. Transition elements or transition metals, whose properties tend to be less predictable based simply on their position in the periodic table. So in the periodic table, there are a total of 18 groups and 7 periods. The groups are numbered 1 through 18, or the A and B grouping. Main group elements are in columns labeled with a number and the letter A, 1A through 8A, or groups 1, 2, and 13 through 18. Transition elements are in columns labeled with a number and the letter B, or groups 3 through 12. So families, groups in the periodic table. Elements within a column are considered families. They have similar chemical and physical properties. They all have the same number of electrons in the outermost shell, or its energy level. Families of the periodic table, we can classify them as alkali metals, which is column 1 / group number 1A, alkaline earth metals, column 2 or group number 2A, halogens, column 17 or group number 7A, noble, or another word is inert gases, column 18 or group number 8A. We'll start with alkali metals. The group 1A elements, called the alkali metals, are all reactive metals. A marble-sized piece of sodium explodes violently when dropped into water. Lithium, potassium, and rubidium are also alkali metals. Alkaline earth metals. The group 2A elements are called the alkaline earth metals. They are fairly reactive, but not quite as reactive as the alkali metals. Calcium, for example, reacts fairly vigorously with water. Other alkaline earth metals include magnesium, a common low-density structural metal, strontium, and barium. Halogens. The group 7A elements, the halogens, are very reactive nonmetals. They are always found in nature as a salt. Pure substances are chlorine, a greenish yellow gas with a pungent odor, bromine, a red-brown liquid that easily evaporates into a gas, iodine, a purple solid, and fluorine, a pale yellow gas. And lastly, noble gases. The group 8A elements called the noble gases are mostly unreactive. The most familiar noble gas is probably helium, used to fill buoyant balloons. Helium is chemically stable, or inert. It does not combine with other elements to form compounds and is therefore safe to put into balloons. Other noble gases are neon, often used in electronic science, argon, a small component of our atmosphere, krypton, and xenon. Ions and the periodic table. Main group metals tend to lose electrons, forming a cation with the same number of electrons as the nearest noble gas. Main group nonmetals tend to gain electrons, forming an anion with the same number of electrons as the nearest noble gas. So in the first example, we have sodium and magnesium. They're pretty close to each other. And in the second part, we have fluorine is very close to neon. Ions and the periodic table. In general, the alkaline metals group 1A have a tendency to lose one electron and form 1+ ions because they only have that one outer electron, so they're going to want to lose it. The alkaline earth metals group 2A tend to lose 2 electrons and form 2+ ions, again because it only has the 2 outer electrons. The halogens group 7A tend to gain 1 electron and form 1- ions. Because atoms are pretty lazy, they're not going to want to lose 7. It's a lot easier to gain 1, and that's why it's 1- because it's gained 1 more negative charged electron. And the oxygen family nonmetals, group 6A, tend to gain 2 electrons and form 2- ions. Again, it's gained those 2 electrons. It's not going to be 2+ because of the gain. It's going to be 2- because it's gained 2 more electrons, which are negatively charged. For the main group elements that form cations, or metals with predictable charge, the charge is equal to the group number. For main group elements that form anions, or nonmetals with predictable charge, the charge is equal to the group number -8. Transition elements may form various different ions with different charges. Atomic mass, the average mass of an element's atoms. Atomic mass is sometimes called atomic weight or standard atomic weight. The atomic mass of each element is directly beneath the element symbol in the periodic table. It represents the average mass of the isotopes that compose that element, weighted according to the natural abundance of each isotope. Naturally occurring chlorine consists of 75.77% chlorine, 35 atoms, mass 34.97 AMU, and 24.23% chlorine-37 atoms, mass of 36.97 AMU. We can calculate its atomic mass as follows. Convert the percent abundance to decimal form and multiply with its isotopic mass. So if we have chlorine-37 equals 0.2423 times 36.97 AMU, we get 8.9578 AMU. Same process for chlorine-35, so we have 0.7577 times 34.97 AMU. That equals to 26.4968 AMU. So we can take those two numbers that we just found, add them together to get 35.45 AMU, the atomic mass. In general, we calculate the atomic mass with this equation. Atomic mass equals sigma fraction of isotope N times mass of isotope N, which equals the fraction of isotope 1 times the mass of isotope 1 plus fraction of isotope 2 times mass of isotope 2, so on and so forth. Mass spectrometry, measuring the mass of atoms and molecules. The masses of atoms and the percent abundances of isotopes of elements are measured using mass spectrometry, a technique that separates particles according to their mass. Molar mass, counting atoms by weighing them. As chemists, we often need to know the number of atoms in a sample of a given mass. Why is this? Because chemical processes happen between particles. Therefore, if we want to know the number of atoms in anything of ordinary size, we count them by weighing. Molar mass of a substance is the amount in grams per mole, where the mole equals 6.022 times 10 to the 23 atoms. The mole is considered the chemist's dozen. Just like a dozen is always 12, the mole is always the mole number. When we count large numbers of objects, we often use units such as 1 dozen objects equals 12 objects, 1 gross objects equals 144 objects. The chemist's dozen is the mole, abbreviated MOL. A mole is the measure of material containing 6.02214 times 10 to the 23 particles. 1 mole equals 6.02214 times 10 to the 23 particles, which is known as Avogadro's number. I would memorize this for the test. It comes in a lot of questions, and it comes in handy for sure. The mole. First thing to understand about the mole is that it can specify Avogadro's number of anything. For example, 1 mole of marbles corresponds to 6.02214 times 10 to the 23 marbles. 1 mole of sand grains corresponds to 6.02214 times 10 to the 23 sand grains. 1 mole of anything is 6.02214 times 10 to the 23 units of that thing. The value of the mole is equal to the number of atoms in exactly 12 grams of pure carbon-12, or C-12. 12 grams of carbon equals 1 mole of carbon atoms, which is 6.022 times 10 to the 23 carbon atoms. Converting between number of moles and number of atoms. The conversion factors take the following forms. We have in the numerator 1 mole of atoms, in the denominator over 6.022 times 10 to the 23 atoms. Or we can flip it, 6.022 times 10 to the 23 atoms in the numerator over 1 mole of atoms. To count atoms by weighing them, we need one other conversion factor, the mass of 1 mole of atoms. The mass of 1 mole of atoms of an element is the molar mass. An element's molar mass in grams per mole is numerically equal to the element's atomic mass in atomic mass units. The molar mass of an element is the conversion factor between the mass in grams of that element and the amount in moles of that element. For carbon, we have 12.01 grams of carbon equals 1 mole of carbon, or 12.01 grams of carbon over 1 mole of carbon, or 1 mole of carbon over 12.01 grams of carbon. The notation may be different, but the concept is the same. So let's look into a conceptual plan. We now have all the tools to determine the number of atoms in a sample of an element by weighing it. First, we obtain the mass of the sample. Then we convert it to the amount in moles using the element's molar mass. And finally, we convert it to the number of atoms using Avogadro's number. The conceptual plan for these kinds of calculations takes the following form. We have, in the first box, grams of element. We have then an arrow pointing to moles of element, and on that arrow it says molar mass of element. And then the next box is number of atoms, and to get from moles of element to number of atoms, we have Avogadro's number. And when we go towards the right, we have multiplication, and then if we want to go the opposite direction, it'll divide. So let's look into a more numerical example of this. Find the number of atoms in a copper rod with a length of 7.65 centimeters and a radius of 1.20 centimeters. The density of copper is 8.96 grams per centimeter cubed. We know that density equals mass over volume, and we have the conceptual plan grams to moles to number of atoms. If we rearrange, we have mass equals the density times volume. And we know that the volume equals pi r squared times the height. This is according to our geometry and trigonometry classes. So pi is 3.142 times the radius 1.2 squared times 7.65, which is our height. The length in this case. After calculating this, we have 34.61 centimeter cubed. We can then take this number, mass equals 8.96 gram per centimeter cube, times 34.61 centimeter cube cancels out, we're left with grams. We get 310.126 grams. This is the mass of the rod. M equals 310.126 grams. This is the mass of copper. Copper is 63.55 AMU. So the molar mass of copper is 63.55 gram per mole. We then take 310.126 grams of carbon times 1 mole of copper over to 63.55 grams of copper to get 4.88 moles of copper. Next step, 4.88 moles of copper times the mole number, or Avogadro's number, 6.022 times 10 to the 23 atoms over 1 mole. Mole cancel it out. We're left with 2.939 times 10 to the 24 atoms of copper. So great. This is a fantastic spot to end it off. And with that is everything I have to share with you today. Please go through the practice problems that your professor may give you. Go through your Pearson online resources, practice, and feel free to listen to this podcast a few times. The mole can be a bit of a tricky concept, but it's a very important concept to get in order to move on to the future lessons. In general, podcasts are a great tool to have, whether you're walking between classes, going on a run, or doing some exercise, cooking or baking, or doing any of your hobbies or volunteering. There are so many opportunities in a day to learn something new and simply magical. I hope you enjoyed today's episode, and I remind you to stay curious.